Our next unit is all about acids and bases and their chemistry. So this video is going to introduce the basics of kind of what makes an acid and what do acids look like. So there are several different definitions of acids and bases, actually. The two that are most applicable to us are what is known as the Arrhenius definition and the Bronsted-Lowry definition. So the Arrhenius definition is that an acid is something that increases the concentration of H3O+, which is known as the hydronium ion, in aqueous solution. So when you put an Arrhenius acid into aqueous solution, the concentration of hydronium increases. The Bronsted-Lowry definition of an acid is that an acid is something that donates H+, also referred to as a proton, since a hydrogen atom without its electron is just a proton. An acid is something that donates a hydrogen ion, aka a proton, to a base. So these two definitions for our purposes are pretty much the same because we are only going to be dealing with acids in aqueous solution. And when an acid is in aqueous solution, water is actually functioning as a base. So a Bronsted-Lowry acid in water is donating its H+ to water, which creates H3O+. So for us, these two definitions are essentially the same thing, but you may hear them referred to. Sometimes you'll hear something referred to as an Arrhenius acid or a Bronsted-Lowry acid, and for us, those are the same. In aqueous solution, those are the same. There are some other definitions as well, but these are the two that we will be working with. So we can see that the definition we're using for acid depends on the presence of hydrogen, that an acid is something that donates hydrogen ions. It donates H+ or a proton to a base, which means it must contain hydrogen. But just any old hydrogen atom is not enough. It must contain hydrogen involved in a polar bond. So not all substances that contain hydrogen are capable of acting as acids. Not even all hydrogens involved in polar bonds are really particularly acidic, but in order to be acidic, they must be involved in a polar bond. So the most common bonds you will see that tend to be acidic are hydrogen bonded to a halogen. So X is how we represent the halogens generally, which are group 7 in the periodic table. So that's fluorine, chlorine, bromine, iodine are our halogens. You also commonly see acids containing hydrogen bonded to oxygen, as well as occasionally hydrogen bonded to nitrogen or hydrogen bonded to sulfur. So we can kind of subcategorize acids and bases as being strong or weak, and we'll talk a little bit more about that in a couple minutes. But these first two bonds are the only ones that are polar enough for our acid to be strong. So these are the most common ones that you'll see. And these are the ones that can be strongly acidic. They're not always strongly acidic, but they can be. These ones you'll see as sometimes weakly acidic. So when we're looking at a formula, we want to start to be able to recognize, is this an acid, is this a base, to understand how something is going to react. So with acids, there is commonly a nice clue in the way the formula is written. So for recognizing acids, just from their formula, most of the time, any acidic hydrogen atoms are written first in the formula. So this is not always like a rule that is obeyed 100% of the time, particularly with organic acids tend to deviate from that. But for the things that we'll be working with, it is typical that any acidic hydrogens are written first in the formula. So a couple examples of things that are acids, H2SO4, and one that I tend to get a lot of questions about, acetic acid, HC2H3O2, that I frequently get asked, why are these H's separate? Why is one out in front and these three are buried deeper back in the formula? And the reason for that is that only one of them is actually acidic. So in our first formula here, H2SO4, in sulfuric acid, both hydrogen atoms are acidic. Both hydrogen atoms are capable of being donated to a base if a base is around. But in acetic acid, there is only one hydrogen atom that is capable of being donated to a base. Only one of them is actually involved in a polar bond. If we look at the structure of acetic acid, it looks something like this in its Lewis structure. We said that hydrogen atoms that are acids, that are acidic, need to be involved in a polar bond, specifically one of these examples up here. And 3 out of our 4 hydrogens are involved in a non-polar carbon-hydrogen bond. So these CH bonds are non-polar. So these hydrogen atoms are not acidic. Oops. But this guy, we have an OH bond, which is highly polar. So that hydrogen is acidic. So this hydrogen out in front is the one that is bonded to the oxygen. These hydrogens in the middle are the 3 that are bonded to the carbon. So whenever an acid is placed in water, it reacts in a predictable way. So all acids react with water in effectively the same way. So I'm going to use a generic representation of an acid, HA. So A for acid, H because we need a hydrogen in there. So when this is in aqueous solution, this reacts with the water that is in there. And we said that acids are proton donors. So that is going to give up H+, and it's going to give it to any base, and water is capable of functioning as a base. Water can be either an acid or a base, depending on what else is around. So in this situation, water is functioning as a base, and bases, which we'll discuss in more depth in the next video, are hydrogen ion acceptors. So the acid is going to give H+ to water, When water gains H+, it goes from having 2 hydrogens to 3, and it goes from having a 0 neutral charge to having a +1 charge overall. The HA, the acid, has lost H+, so it no longer has the H, and starting from neutral, losing a positive charge means that it's going to end up negatively charged itself. So we always get this same type of relationship with an acid in water, where the acid donates a proton to water, generating hydronium and the anion from the acid. So we have names for these things. So after the base gains a proton in this type of reaction, we refer to it as the conjugate acid. After the acid loses a proton, we refer to it as the conjugate base. So the acid turns into the conjugate base, the base turns into the conjugate acid in this type of reaction. So within acids, we have strong acids and we have weak acids. So the strong acids, there is a short list of them. And what makes a strong acid strong, what strength of an acid really is how much of it undergoes this reaction, how much of it actually ionize, what percentage of the acid molecules actually give a proton to a base or to water. So in a strong acid, essentially 100% of acid molecules ionize, meaning that they donate their H+. So that means that that is a reaction that goes to completion, that effectively 100% of our acid molecules undergo this reaction. There isn't any intact acid left at the end. So strong acids are doing exactly the same process here. Oops, brought some extra things with me. Yeah. But it's not really acting like a reversible reaction. It's pretty much going completely in the forward direction. That we can treat this like a situation where we are going to completion, we are completely consuming our limiting reactant. Technically, it's reversible, but the value of the equilibrium constant is in the like millions, billions, trillions kind of territory, is large enough that we can consider all of our reactant to have been completely consumed. So there are only 6 acids, sometimes 7, depending on who you ask, that we consider to be strong in this way. So the list of strong acids is HCl, HBr, and HI, HNO3, H2SO4, and HClO4. Sometimes you will also see HClO3 added to this list. Sometimes you will see HClO3 instead of HClO4. So it doesn't show up too much. Those acids are not super commonly used for a lot of things. Generally speaking, if you need a strong acid, there's a cheaper choice. And they don't get used all that much. So the reaction with water is exactly the same, just going to completion, and that goes for this set of acids here. So A can be chlorine, bromine, iodine, nitrate, sulfate, chlorate, and perchlorate. Weak acids are anything that ionizes less than 100%. And generally, it's a pretty small percentage. So only a small percentage of our acid molecules actually ionize. So that means that in this reaction, we're producing a little bit of product, but most of our stuff stays as reactants. So this is not a situation that we want to treat as going to completion. This is one where we want to think about this as a reversible reaction because it truly is. It establishes equilibrium when only a little bit of product has formed. Weak acids tend to be quite reactant favored in their equilibrium constant. But otherwise, the reaction is exactly the same, that whatever your acid is donates a proton to water, producing hydronium and the conjugate base of the acid. And there is no list for weak acids. It is effectively infinite. Any acid that is not strong is weak. So we talked about how to kind of generally identify acids, that they must have a hydrogen involved in a polar bond. Good clue in the formula is that that hydrogen is written first. If it fits that criteria, so it seems like it's probably an acid, but it's not on this short list, then it is going to be a weak acid, which means that it will establish equilibrium when only a little bit of product has formed.